The universe is speeding up, and nobody knows why. This is the expansion paradox, a profound mystery that challenges the very foundations of physics. Our most trusted laws predicted a cosmos gradually slowing under its own weight. But what we observe is a continuous acceleration, as if space itself possesses a hidden, driving force. By the end of this exploration, you will understand how this single contradiction compels us to reconsider the cosmic ledger and confront a reality shaped largely by the unseen. We will uncover why Einstein once called his greatest idea a blunder, only for it to return as a pivotal insight, and what it means that the vast majority of the cosmos is a complete unknown. How does it change your perspective to know that everything visible is just a small part of a much larger story? For centuries, the deepest assumption about the cosmos was its permanence. A stable and eternal stage where the drama of stars and galaxies played out, unchanging across infinite time. This was the universe Einstein inherited, and it shaped his greatest work. When he applied his new theory of gravity to the cosmos as a whole, the equations told a surprising story. They described a universe that could not sit still. It had to be either growing or shrinking, influenced by its own gravity. This dynamic result clashed with everything astronomers believed they saw. To reconcile his brilliant mathematics with the apparent stillness of the night sky, Einstein made a fateful adjustment. He introduced a new term into the very heart of his equations. He called it the cosmological constant. This was not a force for expansion, but a subtle pressure, delicately tuned to balance the inward pull of gravity. It was a mathematical concept to hold the universe in a perfect and static equilibrium, like a marble resting at the very bottom of a bowl. The idea offered profound comfort. It preserved the ancient and intuitive picture of a cosmos that was simply there forever. Einstein and much of the scientific community could breathe a sigh of relief. The universe was stable as it appeared, but this comfort was an illusion built on a delicate numbers game. The balance was impossibly precise. Shift the scale by the tiniest fraction, and the whole system would either drift apart or gather inward. It was a universe on a knife edge, a cosmic tightrope walk. Decades later, looking back at this elegant fix, Einstein would famously call the cosmological constant his greatest blunder. Why? Because the universe he was trying to force into stillness was already and secretly in motion. A monumental shift was coming, one that would not just adjust a theory, but completely redefine our place in the cosmos. The static dream was about to end. The quiet of that cosmic stage was transformed by a single observation. High on Mount Wilson, astronomer Edwin Hubble spent long nights peering through the world's most powerful telescope, gathering the faint light of distant nebulae. He was not just looking at stars, he was measuring their very essence, the specific colors of their light. What he found was a universal signature of motion. The light from these distant island universes, now understood to be separate galaxies far beyond our own Milky Way, was not the color it should have been. It was stretched, shifted toward the red end of the spectrum. This redshift was the key. It is the same effect you hear when a siren races past you, its pitch dropping as it moves away. For light, that shift in pitch becomes a shift in color. A redder hue meant only one thing. Those galaxies were all moving away from us, but the true revolution was in the pattern. Hubble meticulously plotted the distances to these galaxies against the degree of their redshift. The correlation was stunning and simple. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, painted a picture not of random motion, but of a coordinated, grand-scale expansion. The entire fabric of the cosmos was stretching, carrying the galaxies along with it. It is crucial to understand this distinction. The galaxies are not simply hurtling through a static space like projectiles. Instead, think of space itself as the surface of a balloon being inflated. Draw dots on that balloon, each representing a galaxy. As you blow air in, every dot moves away from every other dot. An observer on any dot would see all the others moving apart, with more distant dots appearing to recede faster. This was the expanding universe. Hubble's discovery transformed our cosmic story overnight. We were no longer residents of a quiet, eternal arena. We lived in a dynamic, growing entity with a history and potentially a future. The universe had an origin point. This revelation answered one monumental question: what is the universe doing? But it immediately raised another, more precise one. How fast is it growing, and will that growth ever change? The answer to that would hold an even greater surprise. Hubble's discovery rewrote the cosmic map, but it also set the stage for an even deeper question. If the universe is expanding, then what is its final destination? For decades, this was not a mystery but a puzzle with a limited set of solutions, a cosmic forecast based on the fundamental laws of gravity. The fate of everything depended on a single, elegant number. Think of it like launching a rocket from Earth. If you give the rocket enough speed, it will overcome our planet's gravitational pull and soar into space forever. But if its speed falls short, gravity will inevitably win, pulling the rocket back down in a long, slow arc. The entire cosmos faced this same simple contest. On one side was the explosive momentum of the Big Bang, the initial push that started everything flying apart. On the other side was the combined gravitational pull of every star, every galaxy, every single speck of matter in existence, all working together to slow that expansion down. The outcome of this grand tug-of-war hinged on a value cosmologists called omega, the critical density parameter. In essence, omega measured the total density of all matter and energy in the universe. This one number would reveal the ultimate destiny of reality itself. The possibilities were stark and beautiful in their simplicity, mapped out by brilliant minds like Alexander Friedman long before we had the tools to measure them. The first scenario was a closed universe. If omega was greater than 1, meaning the density of the cosmos was high enough, gravity would eventually overpower the expansion. Imagine drawing those 3 curves on a graph of cosmic size over time. The curve for a closed universe would rise from the Big Bang, reach a graceful peak, and then bend back downward, tracing a symmetrical arc. All expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward each other. Space itself would contract, growing hotter and denser, culminating in a cataclysmic finale known as the Big Crunch, a mirror image of the explosive beginning. The second possibility was a flat universe where omega was exactly equal to 1. This represented a perfect razor's edge balance. The gravitational pull was precisely strong enough to slow the expansion forever, but never strong enough to stop it completely. On our graph, this curve would rise from the beginning and gradually level out, approaching a state of near stillness over an unimaginable span of time. It was a universe that would coast toward a quiet, cold fade, never collapsing but forever losing its vitality. The third and final destiny was an open universe. Here, omega was less than 1. The density of matter was too low, gravity too weak. The initial momentum of creation would win decisively. The expansion curve on the graph would rise and simply keep rising, never flattening out. The galaxies would fly apart forever into an ever-cooling, ever-darkening emptiness, a fate of infinite, lonely dispersion. For most of the 20th century, this was the accepted framework. The universe's fate was a direct and predictable consequence of how much stuff it contained. It was a clean, logical story, so which destiny seemed most likely? If you had asked any cosmologist before the final years of the 1990s, where would they have placed their bet? The smart money, based on everything we could see and measure, was on a universe slowing down. Gravity was a relentless force, and all that visible matter had to be doing its work. The expansion was surely decelerating, destined for either a gentle coast or a dramatic reversal. This prediction was not a wild guess. It was the unavoidable conclusion drawn from our most fundamental understanding of physics, and that is what made the discovery that came next so utterly shattering. The universe was not following the script at all. To chart the expansion of the cosmos, you need more than a map. You need a ruler, and not just any ruler, but one that can stretch across billions of light years with unwavering precision. For that, astronomers turned to some of the most energetic and brilliant events in the universe, a specific type of stellar explosion known as a Type 1, a supernova. The story of this cosmic ruler begins quietly with a star reaching the end of its long journey. Imagine a star like our Sun, but in its final chapter. It has exhausted its nuclear fuel and shed its outer layers, leaving behind a dense, Earth-sized core of white-hot carbon and oxygen. This is a white dwarf, a stellar ember slowly cooling over eons. But this particular white dwarf is not alone. It has a companion star locked with it in a gravitational dance. And here, the story turns from quiet transition to a tale of cosmic accumulation. The white dwarf's intense gravity begins to draw material, primarily hydrogen, away from its neighbor. This gathered matter spirals down, accumulating on the white dwarf's surface. For a long time, this process is stable, but with every passing millennium, the white dwarf grows more massive, its core under ever-increasing pressure and temperature. It is marching toward a single, inescapable limit. This limit has a name, the Chandrasekhar limit, about 1.4 times the mass of our Sun. It is the maximum mass a white dwarf can support against its own gravity. As the gathered matter pushes the star past this critical threshold, a runaway nuclear chain reaction ignites in a flash. In less than a second, the entire star is transformed in a thermonuclear release of unimaginable power. The white dwarf does not just explode, it is completely transformed in a blast so uniform, so consistent, that it becomes the universe's perfect beacon. This is the Type 1, a supernova. For a few glorious weeks, it can outshine an entire galaxy of 100 billion stars. But its true value is not just in its brilliance, but in its predictability. Because every single Type 1, a supernova, reaches nearly the same critical mass, the physics dictates that every single one achieves nearly the same peak intrinsic brightness. Think of it like a universe-wide network of identical 100-watt light bulbs. If you see one that appears faint, you know it must be very far away. If you see one that appears bright, it must be relatively close. By measuring how bright the supernova appears to us, its apparent brightness, and knowing with confidence how bright it actually is, astronomers can calculate its distance with extraordinary accuracy. These stellar events became known as standard candles, the golden yardsticks of cosmology. In the late 1990s, two independent teams of scientists, the Supernova Cosmology Project and the High-Z Supernova Search Team, embarked on a monumental hunt. They pointed the world's most powerful telescopes deep into space, back in time, searching for the telltale flare of these events in galaxies billions of light years away. Their goal was simple yet profound: to measure how fast the universe was expanding in the distant past and compare it to today. They were not just looking for a speed. They were looking for a change in speed, the deceleration that everyone expected to find. They were about to use the most reliable rulers in existence to measure the shape of cosmic destiny. What they found would not just defy expectation, it would reshape our entire understanding. The data began to tell a story nobody was prepared to hear. As the two teams, working a world apart, meticulously calibrated their measurements and plotted their points on the Hubble diagram, a pattern emerged that defied all logic. The most distant supernova, the ones whose light had traveled for billions of years to reach us, were not where they were supposed to be. According to every model of a decelerating universe, these ancient standard candles should have appeared relatively bright because the expansion back then was presumed to be faster, carrying them to a predictable distance. Instead, they were faint, disconcertingly, persistently faint. This faintness had a single, staggering implication. Those supernovae were much farther away than anyone had predicted. For the universe to have placed them so far into the depths of space, the expansion over cosmic history could not have been slowing down. It must have been speeding up. Team leader Saul Perlmutter of the Supernova Cosmology Project recalled the growing sense of disbelief, saying they spent a year trying to make this result go away. Brian Schmidt, leading the High Z team, described a feeling of profound concern, worrying they had made some colossal error. Adam Rees, a key analyst on Schmidt's team, spoke of the data simply not lining up with the beautiful, slowing universe they all expected. The curve on the Hubble diagram, which should have bent gently downward showing deceleration, was bending upward. Imagine you're driving a car on a long, straight road. You take your foot completely off the accelerator, expecting the car to gradually slow under friction and air resistance. But instead you feel a steady push. You glance at the speedometer and watch, bewildered, as the number climbs higher. That was the sensation in cosmology. The initial push of the Big Bang was the accelerator. Gravity was the brake, and the data was saying that an unknown force had just pressed forward again, billions of years after the journey began. The team subjected their findings to intense scrutiny. Could cosmic dust be dimming the distant starlight? They checked. Could the supernova themselves be different, less brilliant in the early universe? They searched for any evolutionary effect and found none. Every avenue of doubt led back to the same astonishing conclusion. The evidence was solid, and it pointed to an accelerating cosmos. How do you process a result that upends a fundamental belief, one woven into the fabric of physics for a century? You check and you recheck, and then you must accept that the universe is telling you a new story. The announcement in 1998 sent shockwaves through the scientific community. It was not just a new discovery, it was the first direct observational clue that the cosmos was governed by a rulebook we had not yet read. The comfortable forecast of cosmic destiny, with its elegant graphs of closed, flat, or open futures, was suddenly obsolete. A new and profound paradox now stood at the center of everything. The expansion was not slowing, it was accelerating, and for that to be true, something had to be pushing it forward. The faint light of those distant supernovae demanded an explanation, and science found it waiting in its own past. In a profound twist of cosmic irony, the key to the future lay in what had been called a monumental blunder. The cosmological constant, the mathematical term Einstein introduced to hold the universe still and later discarded, was suddenly pulled off the shelf, dusted off, and given a new name. It was no longer a fudge factor. It was now a potential savior, the first candidate to explain the acceleration. Scientists gave it a simple symbol, the Greek letter lambda, and it represented a breathtaking idea. What if empty space itself was not truly empty, but possessed a fundamental, persistent energy density? This energy, woven into the very fabric of the cosmos, would exert a gentle, constant pressure, pushing space apart. It would act as a form of repulsive gravity. Think of the universe as a grand tug of war with two opposing teams. On one side, you have all the matter in the cosmos, from the smallest dust grain to the largest galaxy cluster. This team pulls inward with the familiar force of gravity, working to slow the expansion and pull everything back together. On the other side, you now have lambda, representing this new dark energy. Its pull is not inward but outward. It is a constant, relentless push against the inward drag of matter. For most of cosmic history, matter was densely packed, and its gravitational grip was strong. dominating the contest and slowing the expansion as expected. But as the universe grew and thinned out, the density of matter diluted. The gravitational team grew weaker. Lambda's push, however, does not dilute. It is a property of space itself, so as more space comes into existence, the total amount of this repulsive force actually increases. A helpful analogy is to picture a spring embedded within the fabric of space. Not a coiled metal spring, but a fundamental property that provides a constant outward tension. As the universe expands, it is as if that spring is constantly, gently being stretched, providing an ever-present push that works against the inward pull of all the galaxies. This reintroduction of lambda provided the first coherent theoretical framework to fit the shocking supernova data. It could mathematically produce the upward curve on the Hubble diagram, the one showing acceleration. The mysterious driver behind the expansion paradox finally had a name: dark energy. The cosmological constant, lambda, became the simplest and most elegant explanation for it. This redemption arc for Einstein's idea is a powerful lesson in the humility of science. It shows that our understanding is not a straight line, but a winding path where even our supposed mistakes can contain seeds of future truth. A concept born from a desire to force the universe into a comfortable, static box was resurrected to describe its most dynamic and unexpected behavior. With this framework in place, a pressing new question emerged. If dark energy is real, what exactly is it made of, and how do we prove it is there beyond its shadowy influence on the expansion of everything? That perfect cosmic timepiece, built from the laws of gravity and matter, began to gain time. Imagine a master clockmaker who constructs a magnificent mechanism, every gear and spring calibrated to the finest tolerance. He sets it in motion, confident it will keep perfect time for centuries. Yet when he returns, he finds the hands spinning faster with each passing day. The clock is not just running, it is accelerating, defying every principle of its own design. This is not a minor discrepancy. It is a fundamental breakdown, a signal that a force he never accounted for is now in control of his creation. That is the precise, unsettling nature of the expansion paradox. Our most trusted equations, derived from Einstein's relativity, described a universe governed by a simple contest. On one side, the outward momentum of the beginning. On the other, the inward pull of all gravity from all matter. The predicted outcome was a graceful deceleration. The expansion had to be slowing down, but observation delivered the opposite answer. The data from distant stars did not show a gentle slowdown. It revealed a persistent, measurable acceleration. The universe is not winding down, it is speeding up. This is the core tension, the chasm between prediction and reality. The clock is gaining time, and we must now ask what unseen hand is pushing its hands. To understand the sheer scale of this mismatch, we must look at the cosmic ledger. The equations are like a budget for everything, balancing what is pushing it apart against what is pulling it together. For decades, we only filled in the budget with things we could see or infer. Ordinary matter, the stars, planets, and gas that make up everything familiar to us, accounts for a mere 5% of the cosmic energy budget. Dark matter, the mysterious gravitational glue that holds galaxies together, makes up about 27%. Combined, this matter represented everything we thought was shaping cosmic destiny. Its gravitational pull should have been decisive, but to make the equations match the observed acceleration, to balance that cosmic budget, a new line item had to be added. And it was not a small adjustment. It required a dominant component constituting roughly 68% of everything in existence. This component is what we call dark energy. Think of the universe as a pie chart. For most of human history, we were only aware of a tiny sliver, the 5% of ordinary matter. In the late 20th century, we discovered we were missing a much larger slice, the 27% of dark matter. But the acceleration revealed we were still blind to the largest piece of all, a slice comprising over 2/3 of the entire pie. This 68% was entirely absent from our original calculations. Its omission is why our predictions failed so spectacularly. Mathematically, incorporating this missing majority means inserting a specific value into the heart of the equations. This term acts as a constant energy density of space itself, providing the repulsive push that overwhelms gravity's pull on the largest scales. The required value is not arbitrary. It is precisely the number needed to make the theoretical curves bend upward to meet the data points from those distant stars. This quantitative precision is what transforms a curious anomaly into a profound paradox. The discrepancy is not a small rounding error. It is evidence that the universe is primarily made of something we do not understand. Leading thinkers often call this the most significant problem in fundamental physics today. Why? Because it tells us that roughly 68% of the universe is a form of energy about which we know almost nothing, yet it dictates the ultimate fate of everything. It forces us to confront a humbling question. If we could miss something that constitutes the majority of reality, what other fundamental aspects of the cosmos are we still overlooking? The expansion paradox is not just a puzzle about speed, it is a glaring signpost pointing toward a deeper, unknown frontier. This leaves us with a profound question. What could this dark energy actually be? The first and most elegant candidate comes not from the vastness of space, but from the bizarre subatomic realm. To understand it, we must redefine what we mean by empty space. In our everyday experience, a vacuum is just nothingness, a complete absence of matter. But in the quantum world, true emptiness is impossible. According to quantum field theory, the fabric of space itself is not a placid void. It is a seething, turbulent sea of potential. At scales unimaginably small and for durations incredibly brief, pairs of virtual particles and their antiparticles spontaneously flicker into existence. They borrow energy from the vacuum itself, exist for a fleeting moment, and then annihilate each other, returning the energy. This is not a metaphor. It is a well-established prediction of our most successful physical theory, confirmed indirectly by numerous experiments. This endless, chaotic dance of creation and destruction happening everywhere all the time imbues every single cubic centimeter of what we call empty space with a background hum of energy. Physicists call this vacuum energy or zero-point energy. It is the lowest possible energy state a quantum field can have, and it is never zero. This concept provides a beautifully natural explanation for the cosmological constant. If empty space possesses a fundamental, intrinsic energy density, then it would exert a constant, gentle pressure. As the universe expands and more space comes into existence, the total amount of this repulsive energy increases, driving acceleration. It is a perfect match for the mathematical form of Einstein's lambda. For a moment, it seemed the puzzle was solved. The blunder was not a blunder at all, but a prediction of a deeper reality. The energy of the quantum vacuum could be the dark energy we observe. But then, the theorists did the math. They took our well-tested equations of quantum mechanics and applied them to calculate the expected strength of this vacuum energy. The result was not just a little off, it was catastrophically, incomprehensibly wrong. The predicted energy density was a number so enormous it defies analogy. It was 10 to the power of 120 times larger than the value we actually observe from the accelerating expansion of the universe. That is a 1 followed by 120 zeros. To grasp the scale of this error, imagine predicting that a storm surge would flood the entire planet under an ocean thousands of miles deep. But when you look outside, you observe only a single droplet of water clinging to a blade of grass. The discrepancy is that vast, that extreme. Experts often call it the worst theoretical prediction in the history of science. How can this be? How can a framework as spectacularly successful as quantum field theory, which guides our understanding of particles and forces with breathtaking precision, produce a number so utterly disconnected from reality when applied to the vacuum of space? This is not a minor adjustment. It is a screaming contradiction at the heart of physics. The quantum vacuum candidate, while elegant in concept, does not resolve the expansion paradox. Instead, it deepens it into a chasm. It tells us that either our understanding of the quantum world is profoundly incomplete when applied to the scale of the cosmos, or there is a miraculous, fine-tuned cancellation mechanism we have not yet discovered that reduces an ocean of energy to a mere droplet. The search for dark energy, therefore, becomes a search for something that can either explain this staggering miscalculation or replace the idea of vacuum energy entirely. If the answer does not lie in the quantum foam, then where else could we possibly look? Perhaps the answer does not lie in a static void, but in something that breathes and changes. This leads us to the second major candidate, an idea borrowed from the ancients and given a revolutionary new purpose. They called it quintessence, the fifth and purest element, thought to compose the heavenly bodies beyond our flawed earthly realm. Today, cosmologists have revived this poetic name for a hypothetical dynamic energy field that could fill the cosmos. Unlike the stubborn, unchanging cosmological constant, quintessence is alive with possibility. It is conceived as a type of scalar field, an invisible entity that assigns a single value, a sort of energy level, to every point in space. Think of it like a weather map, but instead of showing temperature or pressure, it charts a subtle, universe-wide energy landscape. The Higgs field, which gives particles their mass, is a famous example of a scalar field. Quintessence would be another, but with a profound difference. Its unique property would be to generate a form of negative pressure, a kind of cosmic tension that acts as a repulsive force, pushing space apart. The power of this model lies in its dynamism. The energy density of this field is not locked at a single, eternal value. It can evolve, slowly rolling from a state of higher potential energy to a lower one, like a ball descending an incredibly wide, gentle hill. In this metaphor, the ball's position represents the field's value, and its speed represents how that value changes over time. The energy associated with the field's current state is what we would perceive as dark energy. This simple picture allows for a fascinating history. In the dense, early universe, the ball might have been perched high on the hill, but its energy could have been negligible compared to the overwhelming radiation and matter. It was a whisper lost in a roar. As the universe expanded and cooled over billions of years, the relative importance of everything else faded, matter diluted. Meanwhile, the quintessence field continued its slow, inevitable roll. Only in the relatively recent cosmic past, as the ball reached a particular part of its long slope, might its energy have become dominant, its repulsive push finally overpowering gravity's grip. This elegantly explains why the shift to acceleration is a late-time phenomenon in our universe's story. We are not seeing a fundamental constant of nature. We might be witnessing a specific chapter in the life of a changing field. This flexibility makes quintessence an attractive alternative. It opens the door to a universe where the expansion rate has a rich and variable history, where dark energy itself could weaken or even change character in the far future. It prompts a reflective question. What if the acceleration we measure today is not a permanent feature of reality, but merely a phase, a temporary push in a much longer and more complex narrative of cosmic expansion and contraction? The idea is compelling because it restores a sense of evolution to the darkest component of the cosmos. Yet, for all its theoretical promise, quintessence currently shares the same fate as the cosmological constant. It is a brilliant idea in search of a fingerprint. While it can be tuned to match the observations we have, it does not yet make a definitive prediction that distinguishes it from a simple, static lambda. The paradox remains alive because both explanations, the constant vacuum energy and the rolling field, fit the current data. The next great breakthrough will not come from theory alone, but from a new generation of observations precise enough to detect the faintest whisper of change in the dark energy's push, to see if that cosmic ball is still rolling. The story of cosmic acceleration is not just about a mysterious push, it is also about a missing pull. Long before we ever suspected dark energy, astronomers were already wrestling with another invisible giant, one that sculpted the universe on a monumental scale. Its discovery began not in the vast emptiness between galaxies, but in the whirling dance of stars within them. In the 1930s, a brilliant and meticulous astronomer named Vera Rubin turned her telescope toward the majestic spiral arms of the Andromeda galaxy. She was measuring how fast stars orbit the galactic center, expecting to find a simple pattern. Just as planets closer to the Sun orbit faster than those farther out, stars closer to the galactic core should zip around much quicker than those on the distant outskirts. Their speed, governed by gravity, should drop off in a predictable curve as you move outward. But the data told a different story. The stars on the outer edges of the spiral were moving just as fast as those near the center. The rotation curve, as it is called, was flat. This was impossible. There simply was not enough visible matter, stars, gas, and dust to generate the gravitational grip needed to hold those speeding outer stars in their orbits. According to the laws of physics, a galaxy rotating that fast should have long ago flung its stars into the void. The only logical conclusion was that something else was there. A vast, unseen halo of matter, exerting a tremendous gravitational pull but emitting no light of its own. This was the first compelling clue for what we now call dark matter. Further evidence poured in from other cosmic vistas. When astronomers looked at giant clusters of galaxies, they saw the same gravitational excess. The visible galaxies alone did not have enough mass to account for how strongly they were pulling on each other, or for the searing hot X-ray gas trapped within the cluster. Then came the ghostly fingerprints of gravitational lensing. Massive objects warp the fabric of space-time, bending the path of light from more distant objects behind them, like a cosmic magnifying glass. The degree of bending revealed that clusters contained far more mass than their luminous parts could explain. Perhaps the most definitive proof came from the afterglow of creation itself, the cosmic microwave background. The precise patterns in this ancient light are a preserved imprint of the young universe's structure. To produce the intricate web of galaxies we see today, the early cosmos must have contained about 5 times more matter than the ordinary atoms we are made of. This matter had to be cold, meaning its particles moved slowly, allowing it to clump together under gravity and form the seeds for all future structure. It also had to be dark, not interacting with light, which is why it remained invisible. This cold, dark matter, making up roughly 27% of the cosmic budget, became the accepted scaffold upon which the visible universe was built. This distinction is crucial for understanding the expansion paradox. Dark matter and dark energy are not two sides of the same coin. They are opposing actors in the cosmic play. Think of dark matter as the master architect and builder. Its relentless gravitational pull is what gathered the primordial gas, sculpted galaxies, and forged the great clusters and filaments of the cosmic web. It is the cosmic glue working tirelessly to pull the universe together. In the grand contest shaping expansion, dark matter is on the team of gravity, applying the brakes. Now picture dark energy as a mysterious, pervasive force field. It does not clump or gather. It is perfectly smooth, spread uniformly throughout space. Its effect is not to pull, but to push, creating a repulsive pressure that stretches the very fabric of the cosmos. In our contest, dark energy is on the opposing team, pressing the accelerator. To visualize their roles, imagine a magnificent stone cathedral. The dark matter is the unseen foundation, and the massive flying buttresses, the hidden structure that holds the entire edifice together against the relentless pull of gravity. The dark energy is not part of the building at all. It is more like a strange, gentle wind that has begun to blow not against the walls, but against the space between the stones, subtly trying to push the entire cathedral apart. For billions of years, the foundation's strength was dominant, but as the universe expanded and the density of matter diluted, the constant push of the wind began to win. The acceleration we measure today is the moment the wind's force finally overcame the structure's innate pull. This makes the observed acceleration even more startling. We have now identified two major invisible components. One, dark matter, constituting over a quarter of everything, is actively working to slow the expansion down. Its presence makes the braking effect stronger than we ever initially thought. For the expansion to not just continue, but to accelerate in spite of this powerful gravitational drag, the push from dark energy must be overwhelmingly potent. It is a testament to the sheer dominance of that mysterious 68%. We inhabit a cosmos where the stage itself, built by an unseen architect, is being stretched apart by an even more elusive force. How do we begin to search for the nature of entities that define our reality yet forever hide from our direct sight? The most powerful evidence for dark energy did not come from watching distant stars explode, but from listening to the faintest whisper of the beginning itself. This whisper is the cosmic microwave background, a bath of ancient light that has traveled for 13.8 billion years to reach us. It is the afterglow of the Big Bang, a snapshot of the infant universe when it was a seething plasma of particles and energy, just 380,000 years old. For decades, this relic radiation was a cosmic hiss, a uniform glow from every direction, but hidden within that perfect uniformity were the seeds of everything to come. The satellites that would find them had names of quiet ambition: the Cosmic Background Explorer and later the Planck mission. Their task was to map the sky in exquisite detail, measuring the temperature of this ancient light to within a millionth of a degree. What they found was a breathtaking tapestry of tiny variations, a modeled pattern of slightly hotter and slightly colder patches. These temperature fluctuations are not random noise. They are the frozen imprint of sound waves that rippled through the primordial plasma, a cosmic symphony played in the first moments of time. To understand what these ripples tell us, think of a calm pond. If you drop a single stone, it creates a perfect set of expanding circular waves. Now, imagine the early universe as that pond, but instead of one stone, it was shaped by a chaotic rain of quantum seeds. Each one created its own set of waves, and all these waves overlapped and interfered with each other. At the moment the universe became transparent, that complex pattern of ripples was frozen into the light, like a photograph of the water's surface at a precise instant. This photograph is the cosmic microwave background. Scientists analyze this pattern by measuring its power spectrum, a graph that shows how common ripples of different sizes are. The key features on this graph are called acoustic peaks, and their size and spacing act as a cosmic ruler of staggering precision. They reveal the geometry of the universe on the largest scales. The logic is beautifully simple. In a closed, positively curved universe like the surface of a sphere, light rays would converge. The frozen ripples would appear larger to us. In an open, negatively curved universe like a saddle, light rays would diverge, making the ripples appear smaller. The measurements from the Cosmic Background Explorer and Planck were unequivocal. The peaks in the power spectrum corresponded to a specific angular size on the sky. That size told a clear story. The universe on the largest scales is geometrically flat. Not closed, not open, but flat. This finding alone was monumental, but it led to an even deeper implication. For the universe to be flat, its total density must equal the critical density, that precise value of 1 we discussed earlier. Yet when cosmologists added up all the ordinary matter and all the dark matter they could account for, they only reached about 32% of the needed density. Something was missing, a huge portion of the cosmic budget, to bring the total to 100% and explain the flat geometry. That missing component, making up the remaining 68%, had to be something that did not clump like matter, something that exerted a smooth, persistent pressure. It had to be dark energy, precisely in the form of a cosmological constant. The cosmic microwave background did not just hint at dark energy, it demanded it. The pattern of those ancient ripples, read with exquisite care, provided a completely independent line of evidence that converged perfectly with the story told by the supernova. 2 different methods, one looking at the recent acceleration of galaxies, the other at the primordial geometry of space, both pointed to the same profound and dominant component. This convergence gave birth to our current standard model of cosmology, known as the lambda-CDM model, lambda for the cosmological constant, or dark energy. CDM for cold dark matter. It is a model of stunning success, able to explain the large-scale structure of the universe, the distribution of galaxies, the abundances of light elements, and the accelerating expansion, all with just 6 key numbers. The cosmic microwave background is its foundational pillar. To look at that modeled map is to see a direct message from the dawn of time, a message that confirms we live in a cosmos whose fate is being written by an unseen hand. How does it change your understanding to know that the oldest light in existence carries within it the signature of our universe's most mysterious future? The infant universe was not a silent place. It was a roaring, seething sea of particles and light, a plasma so dense that light could not travel freely. Within this chaos, a fundamental rhythm was born. Gravity pulling matter inward and radiation pressure pushing outward created a cosmic tug-of-war. The result was a series of pressure waves that raced through the hot soup, moving at a significant fraction of the speed of light. These were sound waves on a scale we can barely comprehend, ripples that compressed and rarefied the plasma in a regular pattern. Then, at the moment of recombination, when the universe cooled enough for atoms to form and light to finally travel free, something remarkable happened. Those sound waves froze in place, their final crests and troughs imprinted into the distribution of matter like a fossilized echo. This is the origin of Baryon acoustic oscillations, a phrase that names one of the most powerful tools in modern cosmology. Baryon refers to ordinary matter, the protons and neutrons that make up stars and planets. Acoustic oscillations are those primordial sound waves. Together, they describe a subtle but detectable pattern woven into the very fabric of the cosmos. For billions of years, this pattern lay hidden, a ghostly template guiding the growth of structure. The frozen wave fronts from the early universe created a preferred scale for where galaxies would eventually form. Matter tended to clump at a specific distance from any given point, the distance that sound could travel in the plasma before the universe became transparent. Think of it like dropping many pebbles into a still pond at the same instant. Each pebble creates a circular wave. When the water suddenly freezes, you would see a complex pattern of overlapping rings. Now, imagine that the ice later melts and new objects, like leaves or twigs, tend to gather along the outlines of those original frozen rings. That is what happened in our universe. The result is that galaxies today show a slight but measurable tendency to be separated by a characteristic distance, a cosmic yardstick etched into the sky. This distance is about 500 million light-years. It is the preserved footprint of an ancient vibration. Finding this footprint required a new kind of cosmic cartography. Projects like the Sloan Digital Sky Survey embarked on monumental efforts to map the three-dimensional positions of millions of galaxies across vast swaths of the universe. They were not just making a picture, they were building a point cloud of the cosmos, a three-dimensional census of its large-scale structure. Within this immense data set, scientists used statistical tools to search for the subtle signal of excess galaxy pairs separated by that specific preferred scale. It is a needle in a haystack of cosmic proportions, requiring extraordinary precision to distinguish from random clustering. The discovery of this signal was a triumph of data and theory. It confirmed that the blueprint of the modern cosmic web was indeed drawn in the first moments of time. This preserved ruler gives us a direct way to measure the expansion history of the universe. The principle is beautifully geometric. We know the actual physical size of the ruler from our understanding of the early universe's physics. It is a standard ruler, just as a Type 1, a supernova, is a standard candle. By observing how large this ruler appears to be at different distances, and therefore at different times in cosmic history, we can measure how much the fabric of space has stretched in the intervening eons. If we look at a galaxy map from when the universe was half its current age, the Baryon acoustic oscillation scale will appear a certain angular size on the sky. If we look at a map of galaxies much closer to us in time, that same physical scale will appear smaller, because the universe has expanded less since the light left those nearer galaxies. By comparing these apparent sizes across cosmic time, astronomers can reconstruct the expansion rate with remarkable precision. This method provides a third, completely independent pillar of evidence. It does not rely on the brightness of exploding stars or the subtle temperature variations in the microwave background. It relies purely on geometry and the frozen imprint of ancient sound. The data from Baryon acoustic oscillation surveys delivers a clear and consistent message. The expansion of the universe transitioned from deceleration to acceleration. The Baryon acoustic oscillation scale measured at different epochs fits perfectly into the model dominated by dark energy. It is as if we found the same set of preserved impressions at different layers of sediment, and by measuring their apparent size, we could chart not just the passage of time, but the stretching of the very ground beneath our feet. To hold this idea is to appreciate a profound form of cosmic archaeology, where the grandest structures we see today whisper secrets about the first noisy moments of everything. Yet this growing consensus soon revealed a subtle but profound crack. Just as the scientific community accepted the reality of cosmic acceleration, a new and stubborn discrepancy emerged, not about the fact of expansion, but about its precise speed today. At the heart of this puzzle is a single number, the Hubble constant, known as h0. It is the current expansion rate of the universe, a value that tells us how fast, in kilometers per second, a galaxy is receding for every megaparsec of distance between us. Determining this number is one of the most fundamental goals in cosmology, and for decades we believed we were honing in on a single, universal truth. But then, our most precise tools began to tell two different stories. One story comes from looking at our local cosmic neighborhood. Teams led by astronomers like Adam Rees, using the Hubble Space Telescope, employ a meticulous technique called the cosmic distance ladder. They start with Cepheid variable stars, pulsating stars whose intrinsic brightness is directly tied to their pulsation period. By measuring nearby Cepheids, they can calibrate their true brightness. Then they find these same Cepheids in galaxies that also host Type 1, a supernova. This links the reliable Cepheid ruler to the brilliant supernova standard candles. By observing these supernovae in even more distant galaxies, they can measure distances and recession velocities with extraordinary care, climbing the rungs of the ladder to calculate h0. This local, late universe method yields a specific, robust number. The other story comes from looking at the dawn of time. The Planck satellite, which mapped the cosmic microwave background with exquisite detail, uses the early universe as its laboratory. The intricate pattern of temperature fluctuations in that ancient light encodes the universe's ingredients and geometry at age 380,000 years. Using the well-understood physics of the early cosmos, scientists can run the cosmic film forward in their supercomputer models. They input the observed conditions from the cosmic microwave background and let the laws of physics simulate 13.8 billion years of expansion, including the influence of dark matter and dark energy. This model predicts what the expansion rate should be today. This early universe method yields a different, equally robust number. Here is the tension. The local measurement from Cepheids and supernovae gives a higher value for the Hubble constant. The early universe prediction from the cosmic microwave background gives a lower one. The difference is not large in everyday terms, but in the realm of cosmology, where measurements are now incredibly precise, it is significant. Statistically, the chance that this gap is due to simple measurement error or bad luck is becoming vanishingly small. Some estimates suggest it is less than 1 in a million. These are not flawed measurements. They are two impeccable clocks, both built with the finest craftsmanship, yet they tick at slightly different rates. One clock was set at the universe's birth, its mechanisms frozen into the cosmic microwave background. The other clock is set by observing the universe today, using stars as its gears. And they disagree. This disagreement is now called the Hubble Tension. It is more than a minor calibration issue. It is a potential paradox nested within the larger expansion paradox. For years, the lambda CDM model, our standard model of cosmology, seemed to explain everything with just 6 parameters. It was a framework of stunning harmony. But the Hubble tension is a persistent, discordant note. It suggests that the model, for all its success, might be incomplete. Could there be an ingredient we have overlooked? Something that changed the expansion rate between the early universe and now. Perhaps dark energy is not a simple constant, but evolved in a way we did not anticipate. Maybe neutrinos, the ghostly particles that stream through everything, have unexpected properties. Or perhaps our understanding of gravity itself needs refinement on the largest scales. The Hubble tension represents a thrilling frontier. It is the sound of a settled story becoming unsettled again. When two of our most trusted cosmic measuring rods disagree so fundamentally, it is not a failure of science. It is an invitation. It tells us that the mystery of our expanding universe still holds deeper layers, waiting to be uncovered by the next generation of telescopes and the bold minds ready to interpret what they see. Perhaps the answer requires a more radical shift in perspective. What if the problem is not with the contents of the universe, but with the very rules that govern it? This leads us to a provocative and elegant alternative. Perhaps Einstein's theory of general relativity, while brilliantly successful in our solar system and in explaining phenomena like black holes, begins to break down on the largest cosmic scales. This is not a fringe idea, but a serious scientific pursuit known as modified gravity. The central proposition is stunning in its simplicity. Maybe we do not need to invent two completely unknown cosmic substances, dark matter and dark energy, to explain our observations. Maybe we just need to adjust our understanding of gravity itself. The most famous of these approaches is called modified Newtonian dynamics, or MND. It was first proposed by physicist Mordechai Milgrom in the early 1980s, directly inspired by the puzzle of flat galaxy rotation curves that Vera Rubin uncovered. Milgrom's insight was not to add invisible matter, but to suggest that the laws of gravity change under conditions of extremely weak acceleration, like those found at the faint outer edges of galaxies. In his formulation, Newton's familiar law of gravity, which says the force falls off with the square of the distance, holds true in our high acceleration neighborhood, like within the solar system. But in the realm of incredibly gentle pulls, where accelerations drop below a tiny critical threshold, the force changes to a different mathematical form. This single adjustment, made at that specific low acceleration frontier, can perfectly reproduce the observed rotation of spiral galaxies without any need for a dark matter halo. It is a compelling piece of theoretical elegance. With one tweak to an existing law, an entire category of mysterious evidence seems to vanish. Of course, explaining galaxies is one thing. Explaining the accelerating expansion of the entire cosmos is another. For modified gravity to be a complete alternative, it needs a full relativistic theory, a version of general relativity that incorporates Mund behavior. Physicists have developed several candidates with names like tensor vector scalar gravity, or TVS. These frameworks attempt to build a new description of gravity where the force's behavior naturally leads to cosmic acceleration at the largest scales, doing away with the need for dark energy as a separate component. The appeal is profound. Instead of a cosmos made of 95% unknown stuff, we would have a cosmos described by a refined, though more complex, set of gravitational rules. To grasp the philosophical difference, consider the metaphor of water. For centuries, people understood water through the physics of waves in a bathtub or the flow of a stream. These rules, like Newton's laws, worked perfectly for everyday scales. But when faced with the vast, turbulent dynamics of an ocean current or a global weather system, those simple rules were insufficient. Scientists did not invent a new, invisible substance to explain ocean currents. They developed a more sophisticated framework, fluid dynamics, which incorporated the same water, but under a new set of equations for a different regime. Proponents of modified gravity argue that cosmology faces a similar moment. We have been applying the bathtub physics of general relativity to the ocean of the cosmos, and it is giving us paradoxical answers. Perhaps we need cosmology's own version of fluid dynamics, a modified theory of gravity that works seamlessly from the scale of planets to the horizon of the observable universe. This path asks us to consider a monumental question. How do you decide when to add new entities to your model and when to change the model itself? The standard model adds two enormous, invisible components. Modified gravity changes one well-established law. Each approach has a different kind of elegance and a different kind of cost. Yet, for all its conceptual appeal, modified gravity faces steep challenges. While it excels at explaining the rotation of individual galaxies, it struggles to account for all the evidence from galaxy clusters, gravitational lensing, and especially the precise pattern of the cosmic microwave background. The lambda CDM model, with its dark matter and dark energy, provides a single, unified framework that explains all these diverse phenomena together. No modified gravity theory has yet achieved that same comprehensive success. Furthermore, overturning a theory as exquisitely tested as general relativity is an enormous undertaking. It has predicted the bending of starlight, the slowing of time in gravity, and the existence of gravitational waves, all confirmed with stunning precision. To modify it is to walk a very fine line, preserving all its spectacular successes while altering its behavior only in the most extreme and least tested regimes. So we stand at a fascinating crossroads with two fundamentally different maps for the same mysterious territory. One map populates the cosmos with unseen giants. The other redraws the lines of force that shape reality itself. The expansion paradox has forced this choice upon us, proving that even our most cherished laws must remain open to question in the face of the cosmos's grandest behavior. The most unsettling possibility is not a static force, but one that grows stronger with every passing moment. This theoretical concept is known as phantom dark energy. It is a variant where the repulsive pressure of dark energy is not constant, as the simple cosmological constant suggests, but actually becomes more intense over time. In the language of cosmology, its equation of state has a specific value less than -1. What this means for the cosmos is not just a steady push, but an ever-intensifying shove. The accelerator pedal is not just pressed, it is being forced down harder on its own with no limit in sight. Some speculative models in string theory and other frameworks allow for such a field, where its energy density could increase as the universe expands, rather than remaining constant or fading away. The implications of this idea transform the future from one of quiet dispersion into a narrative of ultimate dissolution. This path leads to a hypothetical finale called the Big Rip. It is a future singularity, not of crushing density like the Big Bang in reverse, but of infinite stretching. In this scenario, the phantom energy's repulsive force grows so dominant that it overwhelms not just the gravitational pull between galaxies, but every binding force in nature. First, the cosmic web would be severed. Galaxy clusters bound by gravity would be torn asunder, their member galaxies flung into an ever-widening emptiness. Then the expansion would reach into the galaxies themselves. The gravitational glue holding a galaxy like our Milky Way together would be overpowered. Stars would be pulled from their orbits and scattered into the void. As the phantom force continues to amplify, it would eventually target individual solar systems. Planets would be separated from their stars, then it would reach planetary scale. Worlds themselves would be pulled apart. Finally, in the last fleeting moments, the force would reach the fabric of matter itself. The electromagnetic and nuclear forces that bind atoms and atomic nuclei together would be overcome. Every molecule, every atom, every fundamental particle would be pushed apart from every other, separated into non-interacting fragments. The universe would end not with a collapse, but with a silent, absolute separation. Observational cosmologists are acutely aware of this theoretical possibility, which is why a major goal of current and future telescopes is to search for any hint that dark energy's strength is changing. By measuring the expansion history with even greater precision, using supernova, Baryon acoustic oscillations, and other probes, they aim to detect the slightest deviation from a perfect cosmological constant. So far, the data is consistent with dark energy being constant. There is no observational evidence that we are on a phantom energy trajectory. Yet the search continues because the stakes for understanding the ultimate fate of everything could not be higher. To sit with the idea of phantom energy is to confront an existential question on a cosmic scale. It asks us to consider a reality where the very forces that create structure and cohesion are temporary, and where the final act of the universe is one of total separation. This represents one of the most extreme potential resolutions to the expansion paradox, where the mystery of acceleration points not toward a balanced future, but toward an inevitable and dramatic end. It underscores a profound truth in our exploration. The nature of dark energy is not merely an academic puzzle. Its character will write the final chapter for all that exists, determining whether the cosmos fades quietly into cold darkness or meets a far more definitive destiny. The timing of the acceleration presents its own profound puzzle. For nearly 10 billion years after the Big Bang, the cosmos was a story of matter. The density of galaxies, stars, and dark matter was so high that their collective gravity firmly controlled the expansion, slowing it down with every passing eon. Dark energy, if it existed at all, was a whisper lost in the roar, but as the universe grew, matter diluted, its gravitational grip weakened. Meanwhile, if dark energy behaves like a cosmological constant, its push remained steady, a fixed property of space itself. Around 5 billion years ago, a quiet but monumental crossover occurred. The weakening pull of matter and the persistent push of dark energy reached a balance. And then dark energy took the lead. We now live in an era where this mysterious component dominates the cosmic budget, dictating the future of everything. This leads to a question that is simple to ask but staggeringly difficult to answer. Why now? Why do we, as conscious observers, find ourselves alive at this precise and fleeting moment in the 13.8 billion year history of the universe, the very epoch where dark energy has just begun to steer the cosmic ship? From a purely statistical standpoint, it seems like a staggering coincidence. The universe has been matter-dominated for about 9 billion years. It will be dark energy dominated for trillions upon trillions of years into the future, an era of near emptiness and accelerating isolation. The transitional period where the two are comparable is cosmologically brief, a mere sliver of time, and we are here in that sliver. This is known as the cosmological coincidence problem. It feels like arriving at a gathering just as a central moment unfolds, then learning the event has been going for centuries and will continue for millennia. The odds seem infinitesimally small. So, is it just breathtaking luck, or does this timing tell us something deeper about the universe, or even about our own place within it? One compelling line of thought leans toward the latter. Some physicists and philosophers suggest the coincidence is not accidental, but observational. This is an anthropic argument. The idea is that if the universe had many different regions with different properties, a multiverse, then we could only find ourselves in a region capable of supporting complex life. A universe where dark energy dominated too early would have ripped apart galactic structures before stars and planets could form. Life would be impossible. A universe where dark energy was too weak or even attractive might have collapsed back in a big crunch long before intelligent life could evolve. We necessarily observe a universe whose parameters, including the timing of dark energy's rise, allow for our existence. In this view, asking why we live in this special time is like a fish asking why it was born in water. It could not have been born anywhere else. A more grounded analogy is being born on a planet whose entire geological history spans billions of years, but whose climate offers a narrow, temperate window suitable for advanced life. You would not expect to find yourself during the planet's fiery formation or during its future frozen decline. You find yourself in the habitable window, however brief it may be in the grand timeline. Our cosmic epoch may be that window. This perspective does not solve the physical nature of dark energy, but it reframes the coincidence from a puzzle of probability into a clue about the necessary conditions for life itself. It suggests that the very fact we are here to ponder the question imposes a selection effect on what we can observe. Yet, many scientists feel this anthropic reasoning, while intriguing, is incomplete. They search for a fundamental physical reason within a single universe that would naturally lead to dark energy becoming dominant around this time. Could dark energy be dynamically evolving in a way that is tied to the development of structure or the density of matter? Is there a deeper law that couples the two, making this crossover epoch not a coincidence, but an inevitable phase in cosmic evolution? The search for such a law is a driving force behind efforts to detect any change in dark energy's strength over time. To stand under the night sky knowing its expansion is accelerating is to feel a double wonder, first at the sheer scale of the forces at play, and second at the profound rarity of our moment in the story. We live at the turning point, the hinge between a cosmos built by gravity and a cosmos being stretched apart by an unseen energy. This adds a layer of philosophical depth to the physical paradox. The expansion paradox asks what is pushing the universe apart. The coincidence problem asks why we are here to witness the push begin. Together, they suggest that understanding the cosmos may be inextricably linked to understanding the unique and fleeting conditions that allow for questions to be asked at all. Long before dark energy began its slow push, the cosmos experienced an expansion so intense it defies all intuition. In the very first sliver of a second after the Big Bang, the universe is thought to have undergone a breathtaking transformation called cosmic inflation. This was not the steady, gradual growth we see today. It was an exponential event, a period where the fabric of space itself expanded faster than the speed of light, doubling in size repeatedly over a span of time so brief it makes a blink seem eternal. In that fleeting moment, a region smaller than a single proton was stretched to a size larger than our entire observable universe. The driving force behind this phenomenal event was not dark energy, but a hypothetical field known as the inflaton. Picture this field as a kind of cosmic spring wound up with an immense potential energy. As this spring unwound, releasing its stored energy, it generated a repulsive gravitational effect of staggering power, forcing space to expand at an unbelievable rate. The work of physicists like Alan Guth and Andre Linde brought this radical idea to life, proposing inflation not as a wild guess, but as a necessary solution to deep puzzles about our cosmos. Inflation elegantly answers questions that the standard Big Bang model could not. Consider the horizon problem. Look at the cosmic microwave background, the ancient light from opposite sides of the sky. This light has the same temperature to an astonishing degree of precision. But in a universe expanding at a normal rate, these two regions would never have been in contact to exchange heat and equalize their temperature. It is like walking into a large concert hall and finding the temperature perfectly uniform, even though the heaters on opposite walls were never connected. Inflation solves this by proposing that these vastly separated regions were indeed once intimately connected, packed into that tiny, pre-inflationary seed. They were together long enough to reach a common temperature before being moved apart by the inflationary event. Then there is the flatness problem. We observe the geometry of the universe to be remarkably flat. For it to remain so finely balanced for 13.8 billion years requires an initial condition of impossible precision, like balancing a pencil on its tip for eons. Inflation takes any initial curvature and stretches it so dramatically that the resulting universe appears flat to us, just as inflating a balloon makes any small patch on its surface appear flatter. It is crucial, however, to understand how profoundly different this early inflation is from the acceleration we see now. The inflationary epoch was an incredibly brief, unimaginably energetic event in the first fraction of a second. Its driving field, the inflaton, was dynamic and unstable, eventually transitioning to flood the universe with the hot plasma of the traditional Big Bang. In contrast, today's acceleration is a slow, weak, and persistent process that began billions of years later, driven by what appears to be a nearly constant dark energy. Think of the difference between two methods of propulsion. Cosmic inflation was like the explosive ignition of a rocket engine, a powerful, short-lived burst that launched the universe into existence with unbelievable force. The acceleration we measure today is more like a gentle, relentless solar sail, catching a faint but constant breeze that gradually pushes everything apart. One was the tremendous opening act of the cosmos. The other is its quiet, long-term fate. This history raises a fascinating possibility. Does the universe have a habit of undergoing phases of accelerated growth? First, a spectacular inflationary burst to set the stage. Then, after eons of slowing down, a reawakening of acceleration in its later years. Understanding inflation provides essential context for the expansion paradox. It shows us that accelerated expansion is not an unprecedented anomaly in cosmic history. The mechanism, the scale, and the cause are entirely different. But the fact that space can be made to stretch at an accelerating rate is a proven feature of physics. This makes the current acceleration slightly less shocking, yet somehow more intriguing. It tells us the cosmos is capable of such behavior, but it leaves us with the deeper mystery of what trigger is being pulled now, in this quiet, mature universe, to start the stretch all over again. The quest to understand the accelerating cosmos now demands a new generation of eyes, instruments of such power and precision they will map the universe in ways we have only dreamed of. This is not an incremental step, but a leap into an era of cosmic cartography on a scale that redefines the possible. On a mountaintop in Chile, the Vera Sea, Rubin Observatory is preparing to open its giant eye, a mirror over 8 meters wide. Its mission, the Legacy Survey of Space and Time, is a 10-year symphony of observation that will photograph the entire southern sky every few nights. It will not just take pictures, it will create a living, breathing movie of the cosmos, detecting changes and motions across billions of galaxies. Its camera, the largest digital camera ever built, will capture images so detailed you could see a golf ball from 15 miles away. This relentless survey will find millions of distant supernovae, chart the subtle clustering of galaxies for Baryon acoustic oscillation studies, and detect the faint warping of light from weak gravitational lensing on an unprecedented scale. Joining this effort from the vantage of space, the Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer, will peer even deeper with Hubble-like clarity, but over a field of view 100 times larger. Imagine trying to understand the story of a great forest by studying one tree at a time through a narrow tube. Now imagine throwing open the walls to see the entire woodland, its connections and patterns laid bare. That is the power Roman will bring. It will conduct its own vast surveys, meticulously measuring the shapes and positions of galaxies to trace the invisible scaffolding of dark matter and the stretching influence of dark energy with extraordinary fidelity. Meanwhile, the European Space Agency's Euclid mission is already on its journey, positioned at a stable point 1 million miles from Earth. Its specialized instruments are designed for a singular cosmic purpose: to create the most extensive and accurate 3-dimensional map of the universe ever made. By observing billions of galaxies out to distances of 10 billion light-years, Euclid will measure the geometry of the cosmos and the growth of its large-scale structure over cosmic time with a ruler of exquisite fineness. What unites these titanic projects is a multi-pronged strategy, a combined approach to the mystery from every angle. They will harvest millions of Type 1, a supernova, turning them from rare beacons into a statistical ocean of standard candles. They will map the Baryon acoustic oscillation pattern with such density that the preferred scale will stand out like a fingerprint in the data. They will measure weak gravitational lensing, the slight shearing of galaxy shapes by intervening dark matter, to weigh the cosmic web directly. And they will count galaxy clusters, the largest gravitationally bound structures, whose abundance over time is a sensitive gauge of how structure formation was slowed or accelerated by dark energy. Together, these techniques will constrain the equation of state of dark energy, the number that describes its pressure and density relationship. Is that number exactly -1, as a simple cosmological constant predicts, or does it vary, hinting at a dynamic field like quintessence? The difference in the data will be subtle: a slight bend in a curve, a small deviation in a statistical correlation. Detecting it requires the immense, clean datasets these new observatories will provide. This is the equivalent of moving from a magnifying glass to an electron microscope in our study of the cosmos. For the first time, we will not be merely glimpsing the shadow of dark energy. We will be taking its portrait, measuring its influence with a precision that can distinguish between competing theories. The next decade promises a flood of data so profound it will either solidify our standard model or reveal the insights that point toward a revolutionary new understanding. These cosmic detectives, built by human ingenuity and launched into the void, carry with them our deepest questions. What they report back will not just solve a paradox, it will define the next chapter in humanity's oldest story, the story of our place in an expanding universe. The sheer improbability of that one droplet of vacuum energy points toward a staggering possibility. If the laws of physics can allow for a near-infinite range of values, why does our universe exhibit the one specific, tiny number that permits galaxies, stars, and planets to form? One profound answer emerging from the frontiers of theoretical physics is that perhaps our universe is not alone. The extreme fine-tuning we observe might not be a lucky accident, but a simple consequence of statistics in a vast cosmic landscape. This is the hypothesis of the multiverse. The concept springs from some interpretations of string theory, a framework attempting to unify all forces of nature. Instead of predicting a single, unique set of physical laws, string theory suggests the existence of an immense number of possible stable configurations, often visualized as a sprawling, mountainous terrain. Each valley in this landscape represents a different possible universe with its own distinct laws, particle masses, and crucially, its own value for the cosmological constant, or dark energy. In this picture, the Big Bang that birthed our cosmos was not a singular, unique event, but one of countless spontaneous genesis moments, each popping into existence with a random set of physical parameters from this landscape. Thinkers like Leonard Susskind have championed this view, proposing what is known as the anthropic multiverse. The logic is elegantly circular, yet profound. In a near-infinite ensemble of universes, every possible value for dark energy is realized somewhere. In the overwhelming majority of these universes, the value is not the delicate one we measure. In many, dark energy is immensely powerful, causing space to inflate so rapidly that matter never has a chance to clump into stars or galaxies. In others, it might be zero or even negative, leading to a swift collapse. These are sterile, empty, or short-lived realities. But in a vanishingly small fraction of the landscape, the value falls within the narrow window that allows for the slow, gravitational gathering of matter into complex structures over billions of years. And only in those rare universes can conscious observers ever arise to look up and wonder about the value of dark energy. We do not observe a special, finely tuned universe. We observe the only kind of universe we could possibly find ourselves within. This shifts the fundamental question raised by the expansion paradox. It is no longer, why does dark energy have this inexplicably small, non-zero value? The question becomes, why do we find ourselves in this particular part of the cosmic landscape? And the answer, in this framework, is a form of observational selection. A helpful analogy is to imagine walking into the largest library imaginable, one that contains every book that could ever be written, in every possible language and symbol system. You reach out and pick up a volume. The book you hold is not a miraculous coincidence. It is necessarily written in a language you can read and structured in a way your mind can comprehend. You could never pick up a book of complete gibberish or in an alien script because you would not recognize it as a coherent text at all. In the same way, our universe is the one book in the library of reality whose physical constants allow for the story of observers to be written within its pages. This idea offers a powerful, if deeply philosophical, framework for the paradox. It transforms a baffling numerical coincidence into a potential inevitability of our own existence. Yet, it immediately raises a challenging counter-question for science. How can we test such an idea? If other universes are permanently separated from our own, existing in domains beyond our observational reach, does the multiverse hypothesis move from physics into the realm of metaphysics? For many scientists, this is the central tension. The concept provides an elegant explanation for fine-tuning, but risks being untestable, a narrative that explains everything yet predicts nothing unique about our own cosmic neighborhood. Proponents argue that as we refine our understanding of inflation and quantum gravity, we may find indirect signatures, perhaps imprinted in the cosmic microwave background or in the statistical nature of the universe's large-scale structure, that point toward a multiversal origin. For now, it remains one of the most compelling and debated lenses through which to view our accelerating cosmos, a reminder that the solution to our greatest cosmic mystery might ultimately lie beyond the horizon of our own solitary universe. The acceleration we measure today is not just changing the future of the cosmos, it is reshaping it in a fundamental way. One of the most profound consequences of this relentless push is the creation of a cosmic horizon, a point beyond which the universe becomes permanently and utterly unknowable. Right now, galaxies beyond our local gravitationally bound group, which includes the Milky Way and Andromeda, are already slipping away. Their light, stretched by the expansion of space, is shifting to longer, redder wavelengths. As acceleration continues, that redshift will increase until the light from these distant islands becomes so faint, its wavelength so elongated, that it is fundamentally undetectable by any instrument. They will not just appear dim, they will vanish from our observational universe entirely. Cosmologists have described this future state with a poignant term, cosmic forgetting. It is the idea that the universe itself will lose its memory, its history fading from view. The mechanism behind this is both simple and staggering. While nothing can move through space faster than light, space itself can expand at any rate. For points sufficiently far apart, the new space coming into existence between them can accumulate so quickly that the effective separation grows faster than light can cross it. When this happens, any light emitted from that distant point toward us will never arrive. It is like trying to run the wrong way on a moving walkway that is accelerating. No matter how fast you run, you are carried backward. That distant galaxy crosses over an event horizon and is lost to us forever. Let us project this forward on a cosmic timescale. First, the tapestry of the night sky, woven with the faint smudges of distant galaxies, will begin to simplify. Over hundreds of billions of years, one by one, those smudges will redden into darkness. The cosmic microwave background, that ancient whisper from the beginning, will have its photons stretched to wavelengths longer than the observable universe itself. It will effectively fade into a uniform, undetectable radio silence. Eventually, the only objects left visible in the entire sky will be the members of our own merged local group, a single, giant elliptical galaxy formed from the collision of the Milky Way and Andromeda and their smaller companions. To any civilization arising in that far future epoch, the universe will appear profoundly lonely and static. They will see only their own island galaxy, surrounded by an infinite, black and empty sea. There will be no evidence of the cosmic microwave background, no redshifted galaxies to hint at an expanding universe, no clues pointing to a beginning. All the evidence we use today to reconstruct the history of everything will have disappeared over the horizon. To grasp the feeling of this isolation, picture yourself on a sturdy raft, adrift in the middle of a vast, calm ocean at night. You can see the lanterns of other rafts scattered across the water, some near, some incredibly far. These lights are your connection to other voyagers, your proof that you are not alone in the expanse. Now imagine the ocean itself begins to expand, not with waves, but by new water constantly appearing between every point. The rafts themselves do not move, but the space between them grows. At first, the most distant lanterns simply dim. Then, one by one, they wink out, not because they have been extinguished, but because the expanding sea has carried them beyond a horizon where their light can no longer reach you. In time, you are left floating in absolute darkness with no other lights in any direction. Your universe has shrunk to the boundaries of your own raft. You would have no way of knowing that a vast flotilla once surrounded you. This leads to a profound and unsettling question, an information paradox born directly from the expansion paradox. What does this mean for the long-term quest for knowledge, for the scientific understanding of the cosmos itself? We are living in a uniquely privileged era, a narrow window in cosmic time where the universe is both transparent enough to see great distances and still young enough that the light from its infancy and its grand structures can still reach us. We have pieced together an epic story from evidence that will one day be permanently unavailable. Future scientists, no matter how brilliant, may be forever locked inside their island, with no observational data to lead them to the truths we take for granted today. The acceleration that defines our universe's fate also imposes a fundamental limit on cosmic discovery. It suggests that the window for comprehending the full scale and history of the cosmos is not open indefinitely. We are here now at the perfect moment to ask these questions, precisely because the clues have not yet vanished over the edge of forever. A faint pulse of ghostly particles once signaled a cosmic transition. In 1987, detectors placed deep within the Earth registered a brief, precious burst of neutrinos, arriving hours before the visible light from a supernova in a neighboring galaxy. These nearly massless, chargeless particles, born in the heart of the stellar collapse, had streamed directly through intervening matter as if it were not there. That event marked the dawn of neutrino astronomy, proving we could witness the universe through more than just light. Now we are opening an even stranger window. In 2015, a delicate instrument sensed a tremor in the fabric of reality itself, a ripple in space-time from the collision of two black holes over 1 billion light-years away. This was the first direct detection of gravitational waves. Together, these messengers represent a revolutionary new toolkit. They are the quiet observers of cosmology, carrying pristine information across the cosmos, untouched by the dust and gas that scatters and dims starlight. To solve the expansion paradox, we must listen to every whisper the universe offers. Gravitational waves provide something astronomers have dreamed of for centuries, a direct measure of distance without a single rung on a cosmic ladder. The concept is known as a standard siren. Think of the signal from two colliding neutron stars, the dense remnants of ancient suns. As they spiral inward, they emit gravitational waves with a very specific signature. The frequency and amplitude of these ripples tell us exactly how massive the objects are and how they are moving. From the physics of general relativity, we can calculate the intrinsic strength of the gravitational wave signal, how loud it truly is. By measuring how faint that signal appears when it reaches our detectors, we can deduce the distance to the source directly. It is like hearing a perfectly tuned bell ring in the distance. If you know the precise pitch and volume the bell makes, you can tell exactly how far away it is just by how softly you hear it. There is no need to find a similar bell nearby to calibrate it. This is a calibration-free cosmic ruler. The power of this method multiplies when we catch the same event in both gravitational waves and light. When two neutron stars merged in 2017, observatories around the world and in space witnessed the aftermath, a brilliant flash of gamma rays and a glowing kilonova. This electromagnetic counterpart told us exactly which galaxy the event occurred in, giving us its redshift, a measure of how much the universe has expanded since the waves began their journey. By combining the direct distance from the gravitational wave siren with the expansion-derived redshift from the light, scientists could calculate a new, independent value for the Hubble constant. Early results from these multi-messenger events are already providing crucial data, landing intriguingly between the values from the local and early universe methods. While more events are needed to refine the measurements, standard sirens offer a pristine, physics-based path that could one day resolve the Hubble tension, telling us definitively how fast the cosmos is growing now. Meanwhile, an even more elusive background hum waits to be heard. Billions of neutrinos, relics from the first second after the Big Bang, should still permeate every cubic inch of space, forming a cosmic neutrino background. These particles decoupled from matter even earlier than the cosmic microwave background photons. If we could ever detect this fossil sea, it would provide another snapshot of the infant universe from a time before nuclei even formed. Its properties would offer an independent check on the conditions that shape the cosmos, potentially revealing subtle influences on the expansion history that other probes might miss. Detecting it is a monumental technical challenge, as these ancient neutrinos possess incredibly low energy, but the pursuit underscores a fundamental truth in cosmology. When one path presents a puzzle, science seeks another. What does it mean that we are now building observatories not just for light, but for ripples in space and floods of ghostly particles? It reflects the innovative spirit at the heart of the scientific endeavor. The expansion paradox is not a wall, but a signpost pointing toward new methods of perception. We are learning to read the universe in multiple languages. Light shows us the glowing embers. Gravitational waves let us hear the collisions that forged them. Neutrinos may one day allow us to feel the primordial heat. Each messenger carries a piece of the story, untainted by the others. By weaving these threads together, we move closer to a coherent picture, one where the history of expansion is not inferred from a single line of evidence, but confirmed by a chorus of independent voices from the cosmos. The discovery that we are surrounded by a cosmos of invisible forces is a quiet revolution in human thought. It does more than rewrite textbooks. It gently reshapes our most fundamental relationship with reality itself. For millennia, our understanding of the world was built upon what we could see, touch, and measure directly. The sun was a brilliant disk, matter was solid and tangible, and the night sky was a tapestry of lights. The expansion paradox and the dark energy it implies pulls that familiar foundation out from under us. We must now accept that the universe as we directly experience it is a profound illusion, a special effect played out on a stage governed by entities we cannot perceive. What we call normal, the stuff of stars and planets and life, constitutes less than 5% of the cosmic budget. The rest is a complete and utter mystery. This is a philosophical tremor as much as a scientific one. As philosopher of science Karl Popper might have noted, a truly powerful scientific theory is one that makes bold, falsifiable predictions. Yet here we are with a theory, our lambda CDM model, that works spectacularly well but is built upon two giant, unknown pillars. This presents a classic challenge known as underdetermination, where the available evidence can be equally explained by multiple competing theories. Do we add dark matter and dark energy to our inventory of reality, or do we radically alter the law of gravity itself? The evidence does not yet force a single choice, leaving us in a profound state of cosmic ambiguity. This ambiguity is deeply humbling. It enforces a modern version of the Copernican principle, a continuous removal from a position of cosmic privilege. First, we learned Earth is not the center of the solar system. Then, we learned the Sun is a mundane star in a remote galactic suburb. Now, we learn that the very substance of our being, the atoms that constitute every thought and feeling, are a rare and exotic byproduct in a universe dominated by something else entirely. We are not even made of the primary ingredients. To grasp this shift, consider an ant colony living on a single grain of sand. The ants are brilliant. They map every contour of their grain, they understand its chemistry, they build complex tunnels within it, they believe they comprehend their entire world. But their grain rests on a vast beach, which itself borders an ocean whose depth and currents are governed by forces the ants have no capacity to sense. The expansion paradox is our first, faint awareness of that ocean. We have just begun to realize our grain of sand is not the universe. What does this mean for the human drive to know, to understand, to find our place in the grand scheme? It could be seen as a narrative of diminishing significance, a story where we become ever smaller and more marginal. But there is another, more compelling interpretation. It transforms our quest from one of mapping a familiar territory into one of pure, courageous exploration. The mystery is not a wall, but an immense and uncharted frontier. Our curiosity and ambition are not diminished by the scale of the unknown. They are the very tools required to engage with it. The fact that we can pose these questions, that we can build instruments to detect the faint redshift of a galaxy or the ripple from a black hole collision, is a remarkable testament to a different kind of significance. Our meaning may not come from occupying a central place in a cosmos designed for us, but from our unique capacity, here on our tiny grain of sand, to look out and decipher the laws of the ocean. The expansion paradox, therefore, is more than a puzzle of physics. It is a catalyst for a deeper kind of wonder, one that merges scientific awe with a philosophical reckoning, asking us what it means to seek truth in a universe that forever holds its deepest secrets just beyond the light. The search for dark energy is not a solitary quest confined to the silent domes of observatories. Its gravitational pull, so to speak, draws in minds from across the entire landscape of human knowledge. This cosmic mystery acts as a catalyst, a grand challenge that forces innovation far beyond the bounds of astrophysics. To understand an accelerating universe, we must first learn to see it in entirely new ways, and that demand for new vision reshapes the tools of discovery themselves. The most immediate impact is felt in the realm of data. Modern sky surveys, like those conducted by the Vera C. Rubin Observatory, will not simply gather information. They will generate a flood of it, a torrent of petabytes so vast that traditional analysis is impossible. This deluge has made cosmology a primary driver in the fields of machine learning and big data analytics. Scientists are now training artificial intelligence to perform tasks once done by human eyes and minds, teaching algorithms to identify distant supernovae, classify galaxy shapes distorted by gravitational lensing, and find the subtle signal of Baryon acoustic oscillations within oceans of cosmic noise. The techniques refined for these celestial purposes are now filtering into other sciences, from medicine to climate modeling, proving that the need to map the cosmos accelerates our ability to make sense of complex information everywhere. To test our theories, we cannot just look at the sky, we must build universes inside machines. Simulating the 13.8 billion year evolution of a cosmos dominated by dark energy and dark matter is one of the most computationally intensive tasks ever conceived. These are not simple animations, they are rigorous applications of physical law, tracking the gravitational dance of trillions of virtual particles as they coalesce into the web of galaxies we observe. Projects like the Millennium Simulation and its successors require some of the world's most powerful supercomputers, running for months at a time, pushing the very limits of processor speed, memory, and software engineering. The code written for these cosmic laboratories advances the entire field of high-performance computing, solving problems of scalability and efficiency that benefit research in fluid dynamics, material science, and molecular modeling. The universe, in a very real sense, is becoming a benchmark for our technological prowess. This interdisciplinary ripple extends into the pure language of mathematics itself. Describing the complex geometry of an expanding spacetime, the statistical nature of primordial fluctuations, or the nonlinear growth of cosmic structure demands new mathematical formalisms. Cosmologists often work at the edge of known mathematics, developing novel statistical methods to extract faint signals from overwhelming noise, or creating new geometrical frameworks to describe the shape and fate of everything. A beautiful and unexpected example of this cross-pollination involves a technology we use every day. The mathematics central to the JPEG image compression standard, the discrete cosine transform, has a direct lineage to the work of astronomers analyzing the cosmic microwave background. Methods developed to handle the data from those early cosmic microwave background satellites to find patterns in the mottled sky, became foundational to how we efficiently store and transmit digital images across the globe. The mathematics of the Big Bang quietly powers the visual landscape of the Internet. From the glass of telescope mirrors to the silicon of detector chips, the hunt for dark energy refines the very instruments of observation. The need to measure the redshift of incredibly faint galaxies drives advances in spectrometer design. The quest to capture the fleeting light of a supernova a billion light years away pushes the sensitivity of digital cameras to their physical limits. The desire to map the cosmic microwave background in ever finer detail has launched instruments into the deep cold of space and onto the high, dry plains of Antarctica. Each technological hurdle overcome in the name of cosmology becomes a new tool available to other fields, from advanced optics to cryogenics. So when we reflect on the expansion paradox, we might ask a broader question. Is the value of fundamental science measured only in the answers it finds, or also in the new capabilities it forges along the way? The journey to understand why the universe grows faster than predicted is simultaneously a journey that expands the horizons of human ingenuity itself. One of the most persistent questions reveals how our intuition struggles with cosmic reality. If the universe is expanding, what is it expanding into? The answer is not what you might expect, because the question itself is built on a flawed assumption. The universe is not expanding into anything. There is no pre-existing void, no cosmic container waiting to be filled. Instead, the expansion we measure is the stretching of space itself. To grasp this, we must let go of the image of an explosion hurling fragments into a waiting emptiness. That model, while intuitive, is fundamentally incorrect for the cosmos as a whole. A more helpful way to think about it involves geometry. Imagine a vast, infinite grid, like graph paper stretching in all directions forever. Each intersection point on this grid represents a location in space. Now, imagine that the grid itself is being uniformly stretched. The paper is not moving into a larger room. The lines of the grid are simply growing farther apart. Every single point on that infinite grid is moving away from every other point. There is no center to this expansion because every location sees all others receding. This is the essence of cosmic expansion, the increase of the distances between points in the fabric of space over time. This distinction resolves another common misconception, the idea that galaxies are somehow zooming through space faster than the speed of light, violating Einstein's laws. They are not. The speed limit for objects moving through space is absolute, but there is no limit on how fast space itself can stretch. For galaxies separated by vast enough distances, the cumulative stretching of all the space between them can cause their effective separation to increase faster than light can travel. The galaxies are not racing through a static arena. They are essentially being carried apart by the stretching stage beneath them. This is not a violation, but a unique feature of general relativity. Several other ideas naturally arise from this counterintuitive picture. One is the question of whether Earth itself, or our solar system, is being stretched apart by this expansion. Thankfully, this is not the case. On local scales, gravity is an overwhelmingly powerful force. The gravitational bonds holding our planet together, our solar system in orbit, and even our galaxy intact are far stronger than the subtle, large-scale push of expansion. The stretching only becomes dominant in the vast, nearly empty voids between galaxy clusters where gravity's grip is weak. Our cosmic neighborhood is safely bound, an island of stability in an expanding sea. Another point of understanding surrounds the nature of dark energy itself. It is often described as a force, but that is not quite accurate. A force, like gravity or magnetism, acts on objects within space. Dark energy is better understood as a property of space itself, a latent energy density that generates a repulsive pressure. It is not pulling or pushing on galaxies from afar. It is an inherent characteristic of the vacuum that causes more vacuum to come into existence, gently forcing the grid lines of space to stretch. To tie these ideas together, consider the classic analogy of raisin bread dough rising in an oven, but let's use it with precision. The dough represents the fabric of space. The raisins represent galaxies. As the dough bakes, it expands uniformly. Each raisin does not travel through the dough to a new location. It is carried along as the dough around it stretches. From the perspective of any single raisin, all other raisins are moving away, and the farther away a raisin is, the more dough there is between you to stretch, so it appears to recede faster. This captures the key points: the stretching of the medium, the lack of a center, and Hubble's law. Crucially, the raisins themselves do not expand, just as galaxies and solar systems do not expand, because their internal bonds are too strong. Reflecting on this, we might ask ourselves what mental picture we have been carrying. Have we imagined the universe as a firework burst in a dark sky, or as a balloon inflating into a room? These are useful starting points, but they can mislead if we cling to them too tightly. Clear communication is not about dumbing down the cosmos, but about carefully building a bridge from our earth-bound intuition to the stranger truths of reality. By letting go of the simpler, incorrect models, we make room for a more profound wonder, one based not on familiar explosion, but on the silent, relentless stretching of the stage upon which all existence plays out. The universe often reveals its secrets to those who are not looking for them. This is the quiet power of serendipity, the chance discovery that changes everything. The story of the cosmic microwave background, that foundational pillar of our entire model, begins not with a grand cosmological quest, but with a frustrating problem in New Jersey. Two radio astronomers, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna to study celestial radio waves, but their instrument was plagued by a persistent, uniform hiss, a background noise they could not eliminate. They meticulously checked every connection, recalibrated their equipment, and even discovered a pair of pigeons nesting in the antenna. They cleaned out the residue, but the hiss remained. This annoying noise was the same in every direction at all times of day and night. It was not a flaw in their instrument. It was the echo of the Big Bang itself, a whisper from the beginning of time bathing the entire sky. They had stumbled upon the cosmic microwave background. This accidental discovery, for which they later won the Nobel Prize, transformed cosmology from speculation into a precise science. It is a perfect illustration of how the path to profound truth is rarely a straight line. The universe presents clues, and sometimes the most important ones look like nothing more than static or interference, waiting for a prepared and open mind to recognize their significance. This spirit of unexpected discovery runs through the entire narrative of the expansion paradox. The two teams that would eventually reveal the acceleration of the universe, the Supernova Cosmology Project and the High-Z Supernova Search Team, did not set out to find it. Their goal was to measure the opposite, the deceleration they all expected. They were building a better cosmic speedometer to chart the slowdown. They were not hunting for a mystery, they were trying to confirm a settled prediction. When the data began to tell a different story, when those distant supernovae appeared too faint, the initial reaction was not excitement, but profound concern. They spent months, even years, trying to make the anomaly go away, searching for an error in their methods. It was only after exhausting every other possibility that they were forced to accept the staggering reality. The universe was not slowing down, it was speeding up. This is a critical scientific virtue in action, open-mindedness to what the data insists upon, even when it contradicts deeply held beliefs. The story of dark energy is in part a story of scientists listening to a universe that decided to surprise them. This pattern of serendipity is woven throughout cosmic science. Cosmic rays were first detected as mysterious background radiation in early electroscopes, an unexplained effect that led to the discovery of high-energy particles from space. Pulsars, the rapidly spinning neutron stars that serve as cosmic lighthouses, were discovered by Jocelyn Bell Burnell as a bit of scruff, a persistent, regular pulse in her radio telescope data that she initially labeled LGM for little green men before realizing its true natural origin. Gamma-ray bursts, the most energetic explosions since the Big Bang, were first detected by military satellites watching for nuclear tests, their brief, brilliant flashes an unexplained signature from the depths of the cosmos. Think of scientific discovery as a grand detective story. The detective, guided by a hypothesis, follows a logical trail of clues, but sometimes the most crucial piece of evidence is not found at the scene. It is overheard in a cafe or noticed as a smudge on a window, something that seems irrelevant until it connects to the larger puzzle. The prepared mind is the one that does not dismiss the smudge, but wonders why it is there. The hiss in the antenna, the faintness of a star, the scruff on a chart, these are the cosmic smudges that have rewritten our understanding. What does this tell us about the nature of exploration itself? Does it diminish the achievement to know that luck played a role? Quite the opposite. It highlights that discovery is a dialogue with reality. We pose questions with our theories and experiments, but the universe answers in its own way, often pointing toward truths we had not thought to seek. The expansion paradox stands as a monumental example. It emerged not from a direct assault on a known mystery, but from the careful, humble observation of an anomaly during a routine measurement. It reminds us that the cosmos holds wonders not just in its distant galaxies, but in the unexpected turns of the journey to know them. The greatest discoveries often begin not with a eureka, but with a puzzled whisper asking, "What is that strange signal and why won't it go away?" The deepest clues to our accelerating cosmos may be hidden in the smallest possible realms. To truly understand why space itself stretches, we must confront the grandest unfinished task in all of physics, the dream of a unified theory. For over a century, we have possessed two spectacularly successful, yet fundamentally incompatible descriptions of reality. General relativity, Einstein's masterpiece, governs the cosmos on its largest scales. It describes gravity as the curvature of spacetime itself, dictating the orbits of planets, the bending of light, and the expansion of the universe. It is a theory of smooth, continuous geometry. Quantum mechanics, in contrast, rules the domain of the very small, the world of atoms and subatomic particles. It reveals a reality of probability, uncertainty, and discrete packets of energy. It is a theory of discrete, quantized interactions. Both frameworks are exquisitely precise within their own domains, but they speak different mathematical languages and obey different philosophical rules. Where they meet, at the edge of a black hole or the first moment of the Big Bang, our understanding breaks down into paradox. The expansion paradox and the dark energy it implies sits directly at this profound intersection. The vacuum energy puzzle, that staggering mismatch where quantum theory predicts an ocean of energy and we observe only a droplet, is not a minor error. It is a fundamental contradiction, a direct clash between the rules of the quantum world and the fabric of spacetime described by general relativity. Quantum field theory calculates the energy of the vacuum by summing all the fleeting particle interactions allowed by quantum mechanics. General relativity then tells us how that energy should curve spacetime and influence the expansion of the universe. When we plug the quantum calculation into Einstein's equations, we get an answer that is profoundly incorrect. This tells us we are not just missing a number, we are missing the fundamental bridge between these two pillars of physics. The microscopic origin of dark energy, therefore, is almost certainly waiting within a theory of quantum gravity, a single framework that seamlessly merges the very large with the very small. This quest has given rise to several profound candidates. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. Different vibrational modes correspond to different particles and forces. In this framework, gravity emerges naturally, and the hope is that the specific properties of the vacuum, including the value of the cosmological constant, could be calculated from the geometry of extra, compactified dimensions. Loop quantum gravity takes a different path, suggesting that spacetime itself is not continuous, but woven from a network of discrete, quantized loops. In this view, the smooth fabric of general relativity is an approximation of a deeper, granular reality, much like a smooth piece of fabric emerges from a weave of individual threads. This granularity could provide a natural limit that prevents the vacuum energy from reaching an infinite value, potentially yielding the tiny number we observe. A successful theory of quantum gravity would do far more than just solve the dark energy puzzle. It would offer a coherent picture of the most extreme environments in the cosmos. It would describe what truly happens at the center of a black hole, where general relativity predicts conditions that challenge our current models. It would address the famous black hole information question, the puzzle of whether information that falls into a black hole is truly lost forever. Most fundamentally, it would provide a physical description of the Big Bang itself, moving our origin story from a mathematical extreme to a comprehensible physical transition. In this sense, a theory of quantum gravity is the final piece of the physics puzzle. Without it, our cosmic picture, from the first instant to the ultimate fate, remains incomplete. Think of our current understanding as a magnificent, detailed map of a vast continent, but with two major regions drawn in different, incompatible scales. We have a perfect map of the mountain ranges and rivers, the large-scale structure from general relativity, and we have an exquisite map of the molecular composition of the soil and rocks, the small-scale details from quantum mechanics. But we cannot reliably navigate from one map to the other. The border between them is marked only by question marks. Dark energy is a phenomenon that originates in the quantum soil, but manifests as a bending of the entire continental plate. To understand it, we must create a single, consistent cartography. This raises a reflective question for our era of big science and large collaborations. What will it take for a new visionary to emerge, an individual who can see past the established paradigms and perceive a deeper unity? The solution may not come from a lone genius in a quiet office, but from the collective effort of thousands of minds, guided by data from telescopes that see the universe's acceleration and experiments that probe the fabric of spacetime. The quest to solve the expansion paradox is more than a cosmic curiosity. It is a powerful, driving force, a glaring anomaly that compels us toward the ultimate goal, a theory of everything. In seeking to understand why the universe grows, we are ultimately seeking to understand how reality is woven together at its most fundamental level. We stand at the edge of a profound transformation in our understanding of reality. This journey has taken us from the comforting illusion of a static, eternal cosmos to the startling truth of a universe in a runaway expansion, driven by a force we cannot see. We have crossed the chasm between what our most trusted laws predicted and what our telescopes reveal, a space defined by the expansion paradox. Along the way, we have met the candidates for this mysterious driver, from the resurrected cosmological constant and the seething quantum vacuum to the dynamic, rolling field of quintessence. We have seen how independent lines of evidence, the faint light of distant supernovae, the ancient whisper of the cosmic microwave background, and the frozen echo of Baryon acoustic oscillations, all converge to tell the same astonishing story. We have grappled with the stubborn discord of the Hubble tension, and pondered the philosophical tremors that come with knowing we are made of the rarest stuff in a cosmos ruled by the unknown. The ultimate takeaway from all of this is not a simple answer, but a breathtaking shift in perspective. Our universe is not merely stranger than we suppose. It is stranger than we can suppose, dominated by entities and energies we have only just begun to name. This phenomenon is not a flaw in our knowledge. It is a signpost pointing toward a frontier of physics we have not yet reached. This paradox, then, should not be a source of frustration, but a wellspring of inspiration. It is a testament to the relentless power of human curiosity, our unique capacity to look at the night sky, notice a discrepancy, and have the courage to follow it into the heart of a mystery that reshapes everything. The great astronomer and storyteller Carl Sagan once reflected that somewhere, something incredible is waiting to be known. The expansion paradox is the proof of that statement. It is the incredible thing we have found, and yet it is also the gateway to things still more incredible waiting beyond it. This is not an endpoint, but an open invitation. An invitation to keep looking, to keep questioning, to build the next great telescope and write the next revolutionary equation. The cosmos has handed us its most puzzling clue, and the investigation is just beginning. What does this story make you wonder about? Does it change how you see the space between the stars, knowing it is filled with a dynamic, stretching energy? We would love to hear your reflections and questions in the comments below. If this journey through cosmic mysteries has sparked your curiosity, consider subscribing to join us as we continue to explore. The next great revelation is out there, and together we will be here to understand it when it arrives.